It's Rudy, Santiago, Glenn.
And I'm Bounty. This is Team Spider Monkeys. Go for it.
Alright, so we have the generator,
Generator.
the
Tube.
to the rail, streams, the scale, the cart, the bucket sensor, a 10-gram weight, the interface, computer, and then our graphs.
One. We got the nice valleys right there. We're trying to find a machine right now. We once again will use this formula to determine our theoretical acceleration this week. This week we decided to up our hanging mass, or multiply it by 10. So we have 10 grams now as a hanging mass. And using this formula, our acceleration is 0.47 meters per second squared. This is the formula we will be using to calculate the percent difference in our lab. First, percent difference is between our theoretical accelerations, one from last week and the one from this week. Our last week theoretical acceleration was 0.05 meters per second squared. Our new theoretical acceleration with the change in mass is 0.47 meters per second squared. And our percent difference we got for this is 9.3%. Now we calculate our percentage error between our theoretical value, our theoretical acceleration, and our experimental acceleration. With the change in mass, we got our new theoretical acceleration to be 0.47 meters per second squared. During our experiment, getting the mean of the acceleration graph, we got our acceleration to be 0.31 meters per second squared. And calculating the percentage error, we got a percentage error of 34.04%. The final calculations was between our old experimental acceleration and our new experimental acceleration. We would need to find a percent difference between them both. Our old experimental acceleration was negative 0.035 meters per second squared. Our new experimental acceleration was 0.31 meters per second squared. Our percent difference we calculated for this was 9.85%.
Should your old and new percent errors be similar? Why or why not? They should be similar within a certain range. We did use the same materials, same lab, and everything else stayed consistent besides the days that we did it on. So the percent errors shouldn't be too drastically different from each other. Comparing our percent errors, there was some similarities and consistencies between the numbers of the test. They didn't have too much of a drastic change, so there could be a semi-pattern within them. Does a percent error matter if it's small or large, or does not matter at all? Theoretically, we should want the smallest percent error possible, because that means we're as accurate to what is actually happening, which is always the goal. Unfortunately, that cannot be true, with other factors being at play and not just direct numbers. So it does matter, and we would want it to be as small as possible. Does this agree with the idea in the previous question? Why? They should be as small as possible and as close to each other as possible. That is the end goal anytime someone is doing physics. Unfortunately, there are other factors that we cannot account for, and we'll have to have that percent error. The closer we get it to each other and to zero, the better the experiment and the lab and the results will come out to be.
In this experiment, we compared the theoretical acceleration of the system with the experimental acceleration measured during the trials. Based on the results, it is not necessary to rerun both experiments because the experimental values were still reasonable, close to the theoretical values. Even though there was some percent error, small differences between theoretical and experimental results are common in physics. Experiments because real systems are affected by factors that are not always included in theoretical calculations. Between the two experiments, the one that used the larger hanging mass was likely conducted with higher accuracy. This is because increasing the hanging mass increases the net force acting on the system, which produces a larger acceleration. When the acceleration is larger, it becomes easier to measure and the effects of small errors or friction become less significant compared to the overall motion. There are several factors that could have affected the accuracy of the results. One major factor is friction between the glider and the track, as well as friction in the pulley system. Air resistance can also slightly slow the motion of the cart. Measurement errors such as small mistakes in timing or mass measurements can also contribute to differences between the theoretical and experimental values. Additionally, if the track was not perfectly level, that could have changed the acceleration as well. The percent differences between the two experiments do not necessarily need to be the same. However, they should be somewhat similar if the experiment is consistent. In many cases, experiments with smaller forces or smaller masses tend to show larger percent differences between friction and other small forces, have bigger effect on the motion. This is why the experiment with the larger hanging mass often produces results that are closer to the theoretical value. Overall, the results showed that while there is some experiment error, the experiment still demonstrates the relationship between force, mass, and acceleration, and the differences observed can be explained by real-world factors such as friction and measurement limitations.
However, the experiment was not perfect. We observed a percent error of about 34% between the theoretical and experimental acceleration. This tells us that while the pattern was correct, the exact values did not match perfectly. There are several possible reasons for this difference. One major factor is friction on this on the track in the pulley system. Even though the setup is designed to minimize friction, some resistance is always present and can slow down the glider. Another possible error for measurement uncertainty such Another possible source of our error is measurement uncertainty, such as timing inaccuracies, slight variations in how the data was recorded, small differences in mass measurements, or alignment of the equipment could also affect these results. From these values, we can conclude that the experiment supports the theoretical concept, but also highlights the impact of real-world conditions. The system behaved the way physics predicts, but practical limitations introduce some error in the measurement. Finally, let's talk about why percent difference is used instead of numerical difference when comparing results. Numerical difference typically tells us how far apart two numbers are. However, it does not show how significant the difference is relative to the size of the value themselves. Percent difference, on the other hand, expresses the difference as a percentage from the value being compared. This allows us to understand how large the discrepancy is relative to the scale of the measurements. For example, a difference of 0.1 might be large for small numbers, but might be very small for large numbers. Using percentages makes comparison more meaningful and easier to interpret. In summary, our lab 4 results show that increasing the hanging mass increased acceleration as predicted by theory. The percent differences between our results were very similar, indicating consistent behavior in the experiment. Although some error was present, the overall trend matched the theoretical model and demonstrates the relationship between force, mass, acceleration. Thank you. That concludes today's Lab 4 report. Back to you. Thank you for watching. Welcome to Lab 4 Science Report. Today we are analyzing the results of our acceleration experiment and comparing theoretical experimental values to better understand the physics behind the system. Let's start by looking at percentage differences between our values. Our results, the percentage difference between the theoretical acceleration was 9.30%, while the percent difference between the experimental accelerations was about 9.85%. These values are extremely close to each other, differing by less than 1%. Because the values are so similar, it suggests that our experiment behaved in a consistent and predictable way. Even though the setup changed by increasing the hanging mass from 1 gram to 10 grams, the relationship between acceleration and mass still followed the pattern predicted by physics theory. Now we compare these percentage differences more directly. We notice that both are around 9 to 10%. This tells us that the relative change in acceleration remains similar between the theoretical model and experimental measurements. In other words, we increased the mass and acceleration increased in both the predicted calculations and the real experiment at roughly the same rate, as you can see by these charts. This brings us to the next question. Does this agree with our earlier expectations? The answer is yes, mostly. According to Newton's second law, increasing the force acting on a system should increase acceleration. In this experiment, the hanging mass creates the force that pulls the glider along the track. When we increase the hanging mass from 1 gram to 10 grams, the pulling force increased as well, which caused acceleration to increase. Our experimental results showed the same general trend, which means our data supports the theoretical physical model.